Okay, so in this problem we have a simple supported beam that's 30 feet long, and we have this set of moving loads moving from the right side to the left side, and we're trying to find the location of the maximum moment. Well, the first thing we're going to do is find the concentrated or the resultant force and its location. So what I like to do is come down here and redraw it. So I have my 1,200 pound force and my 400 pound force, and just kind of imagine them on a line. Call this point here, say 0. This is 8 feet. First of all, what's the concentrated equivalent force? Yeah, the reaction is just going to be the two values put together. So I got 1,200 pounds plus 400 pounds, which is 1,600 pounds. So somewhere in here is my concentrated equivalent force, 1,600 pounds. That's a funky 6, but you get the idea. And I'm going to say it's some distance x from point O. So what I'm going to do is I'm going to sum moments. Not in equilibrium, they just have to be equivalent. So when I sum moments, and I'll use right-hand rule, I'm going to sum moments about that point O. When I do it for the real force system, I get minus 400 pounds times 8 feet, which is minus 3,200 pound feet. And I do it again now for my concentrated or my resultant force, which would be minus 1,600 pounds times x feet. It needs to be equal to exactly the same. So I can solve for x. What is x? 2 feet. So now I know where it is. So my first case, using this method that we just discussed, is to about the center line of the structure balance the first force and the resultant force. I'll try to draw this a little bit larger. Let's see if I can do it. So here's the center line. So I'll balance it. So on one side I'll have my resultant force of 1,600 pounds, and that will be 1 foot on this side, and 1 foot on the other side is my 1,200 pound force. Then how many feet back to the 400 pound force? Well, from the resultant, it would be 6 feet. You see that? Now the point I'm trying to find the moment is right here. So I'll call that moment 1. So I need to find my reactions, which I haven't labeled this, but let's call this A and B. So I'll have AY and BY. So I think it's pretty simple to see that if you cut the structure here and decide to work the left or the right side, looks like the left side is going to be a lot easier. In fact, all I need to know is AY, right? And I should be able to find the moment here. If I work this side, I'd have an additional force to deal with. So let's do that. So I need to find AY. How do I find AY for this structure? I'm going to sum moments at B. Now here's where you have to make a choice, and I think the choice is a simple one. Do you work the real force system or the equivalent force system? The equivalent force system. You don't do both together. So I'm just going to use the equivalent system. So when I sum moments at B, the only thing that's creating moment about B is my resultant force and AY. So the resultant force creates positive moment. What's the distance from B to that? 14. Well, the whole thing is 30, so the center line would be 15, right? So it looks like it's going to have a moment arm of 14. And then AY creates negative moment with the moment arm of 30 feet. So what's AY equal to? Somebody will have to help me with that. 1600 times 14 divided by 30.
746.7.
746.7 pounds. Okay? So now I cut the structure. Look at the left side. I have my reaction. 746.7 pounds. And I have my internal moment. I'll call it case 1. What's this distance? What's the distance from A to here? 14 feet. So I think you can see if you sum moments that the moment's going to be equal to 746.7 times 14, which is 10,453. And that will be pound feet. So it says that's the moment at that position. Everybody see that? So now I just have to do it again. So I'm kind of run out of room here, so I'll just put a second sheet down, and get it in the right spot, and we'll call that case 2. So again, I'll draw my beam. And I'll locate the center line. Now this time, I'm going to position the second force in the sequence with my resultant force. That has a distance of 6 feet, so that'll be 3 feet. So in that case, I'll have the concentrated or the resultant force here. That's 1,600 pounds. At 3 feet, and then 3 feet behind it will be the 400 pound force. And 2 feet in front of it will be the 1,200 pound force. And where am I looking for the moment? Right there. Call that moment 2. So when I'm evaluating this structure, I have reactions at A and B. And I'm going to cut the structure here. Do I want to work the left side or the right side? Looks like the right side is going to be easier. If I work the right side, I need BY. So when I find BY, I'm going to do what? Sum moments at A. So let's sum moments at A. Make sure I'm in equilibrium. Again, we have to use either the real system or the equivalent system. I think the equivalent system is simpler. So summing moments at A, the resultant force creates negative moment about A, has a force of 1,600 pounds, and a moment arm from here to here. Remember, the total distance is 15 feet. So it looks like it's going to be 12 feet. And then BY creates positive moment at 30 feet. So what's BY? 1,600 times 12 divided by 30.
Negative 640.
Negative?
Oh, sorry, I didn't make that.
Okay, 640.
Yes, sir.
Okay. And now we're working the right-hand side. So I'll draw a free body for that. And on that, we have our BY reaction, which is 640 pounds. And we're looking for this moment here. I'll call it M2. And that distance is 12 feet. So I think you can see the moment at 2 is going to be 640 times 12. What's that? Mr. Isbell, what's 640 times 12? You got 640 in there. Multiply by 12.
76,600.
Say again, 7,000?
690.
So I think you can see that case 1 is the larger of the two cases. So the way we would finish this is I would say the maximum moment in this entire beam is equal to 10,453 pound-feet, and we'll say at 14 feet from A. So that not only tells me the value, but it tells me the location. Any questions about that?
Can you go back to the original drawing?
Sure.
So the way it shows it, just to make sure I'm clear, is on each side of that roller, correct? Where you place the virtual or the resultant load, right? So what's on the left side?
Okay, what you do is you take each load in the sequence. We just happen to have two here. And you balance each load in turn with the resultant about the center line. So if I do the first load, called it case 1, I balanced them about the center line. So I found that distance x1 was 2 feet, so that's why it's 1 foot and 1 foot. They're equidistant from the center line. And then you look under the load. So in the second case, then I'm balancing the resultant load and the second force equidistant about the center line. And I'm looking under that case. So you can see if I had 4, 5, 6, 7, 8 loads, this could be a long process. In terms of an exam problem, 2 or 3. 2 is more likely, 3 is probably stretching it. So any other questions?